Okay, the next aspect of rational functions are going to be a different kind of asymptote. Those are horizontal asymptotes. And again, if you look in your book and look at examples of the graphs, you're going to see what happens as the curve for large x values, and large is a relative thing, you get out about x equals 20, x equals 100, x equals 10,000. That's very large. The y values will typically approach a leveling off, so they'll just be kind of a flat line if it's a horizontal asymptote. And the first one we need to really think about and get into memory banks is f of x equals y equals 1 over x. And I'm putting this f of x equals y just to emphasize that f of x is a y, represents a y. So you always have to ask yourself a question: what happens to y as x goes to infinity? And this is the math way of writing that we're using. So as larger and larger values are inputted into x, what happens to y? Well, on this one, if I put in 2, we get 1 over 2. If I put in 10, I get 1 over 10. If I put in 100, I get 1 over 100. That's already 0.01. If I put in 1 million, 10 million, 50 million, this is going to get really, really small. And typically in math, when we say something's getting small, it's going to approach 0. So in this case, I would have a horizontal asymptote at y equals 0. Okay, it's just the equation of a line y equals 0. Another example, f of x equals 3 over x minus 7. Same thing's going to be asked. What happens as x goes to infinity? Well, as I put larger and larger values in here, yeah, I'm subtracting 7 from them, but I'm still going to get 3 divided by a really big number. That's going to get really, really small. So, well, y approaches 0. The equation of the horizontal asymptote would be y equals 0. And I want you, again, to think about this. That's an equation of a line. It's y equals a constant number. That makes it a horizontal line, so it's a horizontal asymptote. This curve is going to come down or come up to that horizontal line, but never cross it. It's going to approach it. Here's a more complicated one. 3 over x squared plus 5x plus 2. But again, as x goes to infinity, as x gets large, I'm putting a large number in and squaring it. So like if I put 100 in, I'm going to get 10,000 just from that. And then I'm going to add another 500 to it plus 2. 2's not really contributing much. But this is going to get really large quickly. 3 divided by a really large number is going to get really, really small again. So y will approach 0. The equation for the horizontal asymptote is y equals 0. Here's another form. Sometimes you can simplify, and it'll come up with this. Y equals 7 plus 300 over x plus 11. So I have this in yellow for a reason. As x goes to infinity, this term in yellow is going to get small. I don't care what constant I put up here. I could put 30 million up on top here. But as x gets really, really large, that will eventually go to 0. And as this term in yellow goes to 0, what's really left? Well, y equals 7. So that would be the equation of my horizontal asymptote. It would be y equals 7. It's up. Instead of being at 0 here, it's up at 7 there in just a flat line. Okay, so more complicated. F of x equals 9x plus 15 over x squared plus 5x plus 2. I'm going to take that and rewrite it, break it into 2 different fractions. So take a second, look at those, pause this. Notice I put 2 things in yellow. When I look at this term, as x gets large without bound, another way of saying that, this is going to go to 0. So this term is going to get negligible quickly as x gets large. This one, on the other hand, I have this x on top too. So both of these x's are going to infinity, but this one's squared. So when that's squared, it's going to overpower everything else down here because it's the biggest one. So I have to look at the ratio of these 2 yellow terms in yellow. So when I look at that ratio and simplify it, I get 9 over x. Well, think about this simpler ratio. As 9 over x, as x goes to infinity, 9 over x is going to go to 0. So if that's going to 0, then this whole entire function is going to approach 0 for large x. I'm going to have a horizontal asymptote at y equals 0. Now, we could simplify a a lot of this by just, again, looking at these terms right here, 9x over x squared. And I'm going to generalize this next. But if the exponent here, which is a 1, is smaller than the exponent there, which is a 2, so if the top exponent is smaller than that one, this term will always go, this function, excuse me, will always go to 0. So I have some rules here. In general, you can find horizontal asymptotes by looking at the ratio of terms with the largest exponents in the numerator and denominator. If they get ugly, like this one you can see right here, as they get ugly, you can just look at them and see, oh, I have a horizontal asymptote at, and we'll talk about it. If the largest exponent is in the bottom, the horizontal will always be y equals 0, every time. If the exponents are equal, so like this one here, I have 11x squared over 3x squared plus stuff, and I look at the ratio of these lead terms and simplify that, that's going to come up with y equals 11 over 3. So as x grows without bound, this thing is going to level off at a horizontal asymptote of y equals 11/3. And then I have, if the largest exponent is in the numerator, we could have, I'm saying could, because there has to be a special case here, an oblique or slant asymptote. And that will be my next video.